welcome to this video where we're going to have a look at the topic of rates of change. Now this is material which is in your workbook on page 209, and there will be a couple of examples I'm going to ask you to have a look at, but let's have a look at some of the ideas first and we'll work through an example. Okay, so let's jump over to the blackboard here. Okay, so the topic, as I said, is rates of change. Now, you may be wondering why a topic of rates of change when all the differentiation work that we've done is about rates of change. And that is true, and what we're having a look at is really just one specific example of rates of change, which is going to connect the ideas of displacement, velocity and acceleration, which I know are science ideas, but it is an application also of the work on differentiation and integration, so it is also looked at in this topic. So the three terms I mentioned were displacement. So let's have a little bit of talk about these three terms, starting with displacement and then velocity and acceleration. Okay, the idea of displacement, let's say we had a couple of points A and B, and that they were separated by a distance. Let's say they were two towns and they were separated by a distance of 15 kilometers. Okay, and let's put a little bit of compass directions in here. Let's say that that is directly north, and our usual compass directions west and east and south there as well. Now, if we talked about the distance of town B from town A, we'd quite rightly say it's 15 kilometers. So how is that connected with the idea of displacement? Well, displacement and distance are connected, but they're not exactly the same. Displacement is distance, but it adds in also the direction. Okay, so if we talked about the displacement of town B from town A, we would say, well, it's 15 kilometers east of A. So we have the distance, but we also have the direction. And that is also true for these other two terms of velocity and acceleration, where velocity is similar to speed, but it's the speed that something is traveling in a certain direction. Okay, so for example, we might talk about an object traveling, let's say, at 80 kilometers per hour, and let's say its direction was west. Okay, so it's traveling in a westerly direction at 80 kilometers per hour. So velocity also has direction as well as speed. Acceleration is the rate at which velocity is changing, and it is also something where you are concerned with not only the rate at which something is changing its speed. So for example, we might have an object speeding up and increasing its speed of at 10 meters per second every second, so 10 meters per second squared, and it might be also traveling in a, let's say, northerly direction. Now, another thing that's sometimes connected with the direction with both velocity and acceleration, and also displacement for that matter, is that sometimes you see a negative sign for your answer, and a negative in all of these contexts really means coming back towards the origin point. So just bear that in mind, that if something has a negative displacement, it's usually traveling back towards the starting point. Let's say if A was the starting point here. For velocity, it does also mean that it's slowing down. Okay, so negative can mean that as well. and acceleration, if it's negative, means that it is decelerating. Okay, so it is also basically the rate at which its speed is changing is slowing down. So really the negative in terms of direction, probably I more accurately would say that that really refers to displacement coming back towards the origin point, just to make myself a bit clearer on that point. Okay, so to summarize then, if we have displacement and we're wanting to get information about velocity, well, velocity is the rate at which displacement is changing with time. Let me just get rid of that email so it's not such a distraction. Okay, so to repeat myself again, velocity is the rate at which displacement is changing with time. So we get that by deriving. Okay, so we derive, and that is the rate at which displacement is changing with time. Now, quite often, S is used as a symbol for displacement. I suppose it's used because they don't want to mix it up with D for distance, which is something else, which is how far but no direction. V is used for velocity, and so if we get the rate at which displacement is changing with time, ds over dt, that would give us velocity. Acceleration is the rate at which an object's speed is changing with direction. Okay, and we can once again get that by deriving, so dv over dt, and common symbol for that is a. If we go back, then we're going to integrate velocity information to get information about displacement. Okay, so let's have a look at applying this to a particular example. One thing that I would ask you to do as well, please have a read of pages 209 and 210, where there's a couple of good examples given and a little bit of further explanation about some of these ideas that I've just mentioned here. So yeah, please have a read of that as well. Now the example I'm going to have a look at, and I will swap over here to a clean page, is the the question 185 on page 211. Now in this particular example, we're told that we've got a car traveling at 100 meters per second, and the driver then brakes. And we're told that the acceleration is given by this equation as a quadratic, 3t squared minus 12t minus 15, and the units are meters per second squared. Now, just would want to point out here with this question and others like it, basically if you're not told anything else, then t, where does t start? Well, it starts from the beginning of the description, where when the description is given, it begins at that point. So sorry, that sounds a little confusing. So the driver brakes, so t time starts from the moment the driver put his foot on the brakes, or she put her foot on the brakes. Okay, so t is usually given from the beginning of the situation described. Okay, and the first question says, what is the acceleration at t equals 2? Now, you don't always have to apply differentiation and integration, depends on the question, and here we're simply wanting the acceleration, and we've got a given by this formula when t equals 2, so we're simply going to substitute that t equals 2 in. Now if you do that, you would calculate this equation here. Then even looking at that, you might realize that the answer is going to be negative, so negative 27 meters per second squared. And it says, why is the acceleration negative? Okay, that's the question in B. Why is the acceleration negative? Well, when you've got a negative acceleration, it actually means deceleration. So in other words, the car is slowing down at 27 meters. So the speed, or the velocity, is going down at 27 meters per second every second. So i.e. the car is slowing down, decelerating. Okay, moving on to C. What is the velocity function? Well, here we actually are going to need to do some integration. If I just jump back to that previous screen, we've got acceleration information, we want velocity, so we need to integrate. And don't forget, there will be that constant of integration, so we're going to have to deal with that. So velocity will be given by the integral of this question here. And so let's integrate. And this is just basic power rules, and I will just tidy that up. Okay, just double checking that looks okay. Now how are we going to find this constant? Well, one thing that we were told right at the start was the car was traveling at 100 meters per second when the driver hit the brakes. So in other words, at t equals 0, okay, the velocity was 100. So that means we can substitute the 100 in for v, and if you put 0, 0, 0 in each of those time places, then C would come out to be 100. So just moving over here, I've got a bit more room, just finishing off C. Our complete velocity equation should be t cubed minus 6t squared minus 15t plus 100. Okay, D asks, okay, how long does it take for the vehicle to stop? And maybe thinking, oh well, that's something to do with distance. No, not really. If you think about that a little bit more, you'd realize that when a vehicle stopped, its velocity would be 0. So what this question is about is really saying, when does this velocity equation equal 0? Now there are certainly numeric methods you could use here, or algebraic methods to solve that, but I've just grabbed a calculator and got two answers, t equals 5 and negative 4. Now since t equals negative 4 is before we started timing, the only sensible solution here is t equals 5. In fact, it's not a solution, the other value of t, to make that clearer. therefore doesn't make sense in this context. Okay, so how long for the vehicle to stop? 5 seconds. And to finish off, E, find the displacement function and how far the vehicle travelled from applying the brakes until stopping. Well, we know it stopped after 5 seconds, but we haven't got the displacement equation, and that means integrating our velocity one. If you jump back to this page again, velocity, how do we get displacement information? We've got to integrate again. So let's integrate our velocity function. Okay, so for this here, that will be 6t cubed over 3, which will become 2t cubed minus 15t squared over 2 plus 100t and a constant. Now you can call that c, but if that confuses you because you've already got c over here, we'll just call it something else like k for constant. Now how are we going to find that? It doesn't seem like we've been given any distance information, and at first sight that seems to be true, but let's go back to the description given. Okay, it was the vehicle traveling at 100 meters per second when the driver hit the brakes. So if you think about that, and given that t is the instant that the driver hit the brakes, the car won't have traveled any distance or displacement at that instant when time has first started being recorded. So what we're saying here is at the instant we start recording, the displacement of the vehicle is 0. Okay, and that would mean therefore that k would also equal 0. Certainly after a second or two the car will have travelled certain displacement, but at that instant we start recording, the displacement would have to be 0. Okay, so therefore we've got our displacement equation where the constant at the back was just 0. Okay, and the last part of that question was how far the vehicle travelled from applying the brakes until stopping. Well, we know it stopped after 5 seconds. We got that from the answer to D. Okay, and therefore when we substitute 5 into the displacement equation, which is what this means, okay, then that would mean that we've got to put the 5 into here. Okay, and calculating that is something I'll get you guys to do. Sorry, my pen is not behaving very well here at the moment. Okay, and that should come out to 218.75, and the units would be meters. Okay, so that's an example worked through. Now guys, what I'm going to do is I'm going to put in one question into the video, and actually I'm going to ask you to do one of the questions from your workbook but to put the answers into the video. Now I know you can simply look at the back then and see what the answers were, but it asks you to actually try and just work through that without looking at the answers in the back of the book. And the question I'm going to get you guys to do is question 183. So I'll describe that in the video, so enter your answers into the video at the places indicated when you get to it. Okay guys, good luck with that. Catch you in class tomorrow.